Now, in order to do division of complex numbers, we need to explore this idea of the complex conjugate a little more. Now, we've already seen that in a previous example, that when you multiply a complex number by its conjugate, which is, as you can see here, okay, if we've got z equals x plus yi, then its complex conjugate is x minus yi, okay, and the complex conjugate is denoted by z with a little bar over the top. And we've already seen that when you multiply a complex number by its conjugate, that we get a real number. Okay, have a look through this. This is a formal proof that that is the case, even though we've seen it in a previous example. Now, this is an important result, as we need to use that in order to divide by a complex number. Okay, so let's have a look first of all at, again, just another example of a complex conjugate. Okay, we just have this complex number, z equals 2 plus 5i, write down the complex conjugate and then find the multiplication of z times its conjugate. Now, if z equals 2 plus 5i, then simply its conjugate is 2 minus 5i. Now, from the previous proof here, if we multiply a complex number by its conjugate, it is simply the real number squared plus the real part squared plus the imaginary part squared. Okay, so our real part is 2, our imaginary part is 5, so the multiplication of the complex number by its conjugate is 2 squared plus 5 squared, which is 29, a real number. So how are we going to apply that a little further? Well, we're just going through and just proving a little point here. If we have z equals 5 minus 2i and w, a different complex number, is 7 minus I, show that the complex conjugate of z plus w is equal to the sum of their individual conjugates. And so as we work through that, z plus w we find is 12 minus 3i. Now, if this statement is true, okay, z plus w, the complex conjugate of z plus w, is equal to their individual sums of the conjugates, the best way to do these proofs are to look at the left-hand side and see if the right-hand side equals that. So the left-hand side, the complex conjugate of the sum of z and w, well, we've already worked out the sum of z and w, that's 12 minus 3i, so its conjugate is 12 plus 3i. Now if we look at the right-hand side, the conjugate of z plus the conjugate of w is 5 plus 2i plus 7 plus I. Adding the real parts we get 12, adding the imaginary parts we get 3i. So it's 12 plus 3i, which is equal to the left-hand side. And so we've proven this result. Let's move down. And this is what we're really getting to now, is that when we're dividing by a complex number in the form of a plus bi, we multiply the numerator and the denominator by the complex conjugate of the denominator. And this will ensure that we get a result in the form of a plus bi without having any imaginary numbers in the denominator. So let's look at this particular example. We want to express this division in the form of a plus bi, and that means that we don't want any imaginary numbers in the denominator. So our process of division is to multiply the top and bottom by the complex conjugate of the denominator, which is going to be 2 plus I. So we can see that here, 2 plus I over 2 minus I multiplied by 2 plus I over 2 plus I. And so we have in our numerator 2 plus I squared, or 2 plus I times 2 plus I. The denominator is 2 squared plus 1 squared. And so we have on the top here, when we expand this binomial product, 4 plus 4I plus I squared over 4 plus 1, which is 5. And working this through, I squared is negative 1, so that's 4 minus 1 is 3, plus 4I over 5. Now to write it in this form, A plus BI, we'll split this into 2, 3 over 5 plus 4 over 5I. Now what we're going to look at now is something called the multiplicative inverse of a complex number. Now we're used to working with the multiplicative inverse already of real numbers, and that simply achieves the result of 1. So if we think of a couple of examples, the multiplicative inverse of 2 is 1 over 2, because when we multiply them together, the 2's cancel and we're left with 1. Also 3/4, its multiplicative inverse is going to be 4/3, because when we multiply those together, the 3's cancel and the 4's cancel, and we're left with 1. Okay, the multiplicative inverse of a real number is its reciprocal. The multiplicative inverse also exists for a complex number, and we denote it as z to the negative 1. And so z to the negative 1 being 1 over z, and if z is defined by a plus bi, then if we've got z to the negative 1, it's going to be 1 over a plus bi. And in order to change this so that we've got no imaginary numbers in the denominator, then we multiply by top and bottom by the complex conjugate of the denominator, and so we find that we end up with a minus bi when we multiply it on top, and on the bottom we have a squared plus b squared on the bottom. And so we just look at a couple of examples, find the multiplicative inverse of these complex numbers. So 3 plus 4i, it's going to be the conjugate on top, 3 minus 4i, and on the bottom 3 squared plus 4 squared, which turns out to be 9 plus 16, which is 25. Splitting that, we get 3 over 25 minus 4 over 25i. Multiplicative inverse of w, which is 2 minus 5i, its conjugate on top, 2 plus 5i, and in the denominator we have 2 squared plus 5 squared, which is 29. Splitting it into 2, we have 2 over 29 plus 5 over 29i. Now, we may also solve complex number equations. Okay, so we're just gradually working our way towards some more complicated complex number calculations. Now let's have a look at this particular example and see how it works through. So we've got this situation where we've got 5z minus 15 over z minus 1 equaling 4 minus 3i. Now, if z is the complex number a plus bi, we want to find what the values of a and b will be for this to be true. There are a couple of methods involved in working this through. Let's look at this particular method here. Let's work through the problem as one would normally solve an equation. So we'll make z the subject of the equation. So we're going to ignore the fact that z is a plus bi for the moment, and we're just going to go through and solve for z. So in order to do that, we get rid of this denominator, multiplying both sides by z minus 1. So on the left hand side we have 5z minus 15, on the right hand side we have 4 minus 3i times z minus 1. Left hand side stays the same, and on the right hand side we expand this binomial product, so that we end up with 4z minus 3iz minus 4 plus 3i. Underneath that, okay, what's happening now is that we're collecting all our z terms over to the left hand side, and any other term has come over to the right hand side. So on the left then, 5z minus 4z is z, and so we've got z plus 3iz on the left, and on the right we have minus 4 plus 15, which is 11, plus 3i. Left hand side, because we want to solve for z, we're going to take z out as a common factor, and so that gives us z outside of 1 plus 3i. Right hand side stays the same. Solving for z, we want to divide now by 1 plus 3i. So z equals 11 plus 3i over 1 plus 3i. And so what we're going to be doing now is to multiply by the complex conjugate of 1 plus 3i. And in so doing, expanding the top, we get 11 minus 33i plus 3i minus 9i squared. And on the bottom we have 1 squared plus 3 squared. The top simplifies to 20 minus 30i, and the bottom is 10. Splitting that, 20 over 10 gives us 2, minus 30 over 10, which is minus 3i. And so if z is a plus bi, then a, our real part, is 2, and b, our imaginary part, is negative 3. So that's the first method. The second way we could do it would involve replacing z with a plus bi in the original equation, then collecting all the terms with a and b onto one side of the equation and all other terms onto the other side of the equation, and then equating the real and imaginary parts. So in doing that, we'll still start off by putting z minus 1 over to the right hand side, as we have done here. That was the same as the first step in the previous method. Then what we'll do is replace z on the left and right with a plus bi, and so we can see how that's replaced here and here. Expanding, we get 5a plus b, 5bi minus 15. On the right hand side we have 4a plus 4bi minus 4 minus 3ai minus 3bi squared plus 3i. We're going to collect all our a's and b's over to the left hand side, as we can see we've done here. All other terms onto the right hand side. Simplifying that and collecting it so that we've got our real parts here, our imaginary parts here, and now we're going to equate them. So a minus 3b equates to 11, because remember, if two complex numbers are equal, the real and imaginary parts must be equal. So a minus 3b must be equal to 11, and 3a plus b must be equal to 3. And then we've got some simultaneous equations that we can solve. And so doing, we find a equals 2 and b equals negative 3. So now what I want you to do is having watched that video, again, work through these problems yourself. Make sure you can follow the steps, you can do them yourself. And then when you're happy with that, work through the text, exercise 3C, and do those problems there. Okay, well done. Thanks for listening.